Okay, let's start with the natural frequency. What's the meaning of the natural frequency? Can anyone heard that? Have you heard about this natural frequency in any lesson? For example, Yağmur.
Means like without an external force.
Without an external force and time. It's the unique parameter for the what? For the any model or the any system or any mass or any device. For example, the Galilei pendulum model. Just remember that we have the what? The rod with the length of the L, right? And so we have also a spring, right? And then this pendulum rotates or has a period about the what? About the in terms of the what? The L and the K value, the spring factor, right? It's unique for the what? For the any device or the any model or the any mass spring damper system. Okay? The natural frequency is the what? The body frequency, but its internal parameter. For example, Yağmur has specific natural frequency. Okay? And what's your name again? Abdullah. Abdullah has the specific or the unique natural frequency because the Abdullah has the mass and Abdullah has the spring factor in the time, right? And so consider this system, right? The system of the what? M x dot dot plus k times x is equals to the 0. Okay? And so the M is the mass, K is the spring. And so we can solve this problem with the what? With the taking the Laplace transform of this domain, right? And so the M times S square times xs minus sx0 minus v0. This is the unique property for the what's coming from the Laplace transformation for the what? X dot dot. But with the initial conditions, x0 is the position, v0 is the what? The velocity values. Okay? And so plus k times xs is equals to the 0. Okay? And so we can collect the whole term of the xs in here, just like this one, m times s squared plus k equals to the what? We have this position and the velocity value. We should put the right hand side of this equation and then the msx0 plus mv0. Okay? And so the xs can be represented by with the what? With these terms. msx0 plus v0 divided by ms squared plus k. Okay? Or we can divide each term into the what? Into the m values. Okay? And so sx0 plus v0 and s squared plus k divided by m. And so the k divided by m is a unique property for the what? For this mass spring damper system. But in this case, mass spring system. Because we don't have any loss energy in here. Because we don't have the damper. C. Right? And so this Km is the natural frequency value in terms of to what? To this one. This Km is equalized with the what? The omega n square. Okay? This is intended because if we solve this xs equation and then we can collect the whole terms. The xs is equals to what? The x0 times s plus s square omega n square. Okay? And also we can collect the v0 Wn times Wn divided by S square plus omega n square. Okay, and so this is the useful property to obtain the time response characteristics for this equation. In Laplace domain, this is a special function to represent the cosinus Wn(t). Okay, if you want to solve it, this equation, and then this equation returns to at this domain the cosinus W times t, right? And so what is this? Can anyone guess that? Huh? Eh? Sine, yes, sinus, sin Wn(t), which means that if we have these two terms in here, and so our time response is oscillate with the frequency of the what? Huh? Who is talking? Huh? What's your name? Aziz. Aziz, yes. Wn is our frequency, right? At this case. See? And so we can always oscillate between these two values, okay? Because we don't have any loss energy, or we cannot consume the energy in here. We store the energy, and so at each case, the cosinus and sinus creates the oscillation pattern for this case. But our oscillation pattern is equal to the k divided by m, but in the square form, right? Square root of the k divided by m. And so our solution looks like this one. X is 0 times cosinus Wn(t) plus V0 divided by Wn times sinus Wn(t). Okay? And so, how can we define the natural frequency? This is the radian frequency of the free response, right? What is free response? What's your name? Yes, Ulash. Ulash, what is free response? I don't. And so anyone knows that free response, free, yes,
related to the initial condition.
Yes, initial condition. And so if we don't have any forced response, or the input signal, or the input signal is equal to the 0, and so if we have any initial condition like the x0 and v0, and so our model oscillates from from these conditions. And so the natural frequency is the frequency value or the period of this oscillation. It's represented to this one, okay? And so can anyone say about the resonance? What is the resonance? Aziz, what's your name? Mentala. Mentala. What is resonance?
It's where your XL is equal to XC. It's where the XL is equal to XC.
I don't
It's
know.
where the frequency of the capacitors is equal to the frequency of the inductor.
Yes, but the resonance in the basic definition is that. For example, this table has a resonance, okay? But the resonance frequency, or the resonance frequency is higher, more than the 1000 or 2000s, right? Because we have the m value, and this is the this is the flexible, because it can bend, just like this one. The k value is greater than this one. For example, the 100,000th k value is contained in here, okay? And so, if I apply this force with this frequency, for example, 1, 2, 3, 4, 5, 6. And so my frequency, Ulaş, is that the 1 hertz, right? 1, 2, 3, 4. But maybe I can apply the force just like this one. 1, 2, 3, 4, 5, 6, 7. And so at this case, we have the 2 hertz, okay? And so the bending or the displacement of the table does not change in here. But if I choose my hand frequency is equals to the Wn, for example, maybe it's 1000 hertz in here. If the table natural frequency is equals to the what the input frequency, and so at each pulse, just like this one, accumulates on the displacement. And so this displacement at each case greater and greater than to what? To previous one. And so it goes to the what? The infinity value. Okay? And so this is called the resonance at W and input signal. Şimdi Türkçe'de anlatayım. Rezonans ne arkadaşlar burada? Bu tablanın frekansı var ya. Bu frekans mesela 1000 Hz olsun. Eğer ben 1000 Hz'lik böyle bir şey yaparsam, küçücük bir kuvvet uygulasam bile burada hep bu ne olacak biliyor musunuz? Daha da displacement'ını arttıracak. Böyle artacak. En sonunda bu kırılacak. Anladınız mı? Mesela köprüler falan çöküyor ya. Neden çöküyor onlar? Rezonanstan, rüzgardan değil. Rezonanstan çöküyor. Rezonanstan çöküyor. Ne? Tabi orada da mesela bir frekans oluşuyor. Ama mesela bak hep böyle nasıl bir örnek verelim mesela? Mesela bir tabur asker köprünün üstünde yürüsün. Değil mi? Onlar mesela 1, 2, 1, 2 ritmik gidiyorlar ya. Her seferinde küçücük bir kuvvet, 2 Newton'luk, 5 Newton'luk kuvvet hep birikiyor. Birikiyor. Artık köprü sallanmaya başlıyor. O yüzden mesela insanlar ne yapıyorlar? Doğal frekansı öyle bir seçmeye çalışıyorlar ki arabalarda ya da atıyorum işte köprülerde o frekansla hiçbir giriş oraya yapılmasın mesela. Değil mi? Mesela arabanızı çalıştırın. Arabayı çalıştığınızda düşük devirlerde araba sallanmaya başlar mesela. Niye sallanmaya başlar? He? Hayır. Hiç alakası. Doğal frekans mesela orada belki 3 Hz 4 Hz mesela bir tane doğal frekansı sizin motorunuz 4 Hz'de dönmeye çalışıyor orada. Araba hani dururken mesela kendi kendine böyle bir sallanıp bir durur ya aslında ondan yapıyor bunu. If your car is run at a low speed, for example, if you push the start, and so we have at the beginning to the what the 1 Hz or the 2 Hz or the 4 Hz for the speed rotation of the motor, right? And so at this case our car is shaking. But if we push the gas, and so it's diminished. The vibration is removed, eliminated, right? And so this means that we have the low value natural frequency at our car, right? The input signal is the rotation of our motor. Abdullah, do you understand this example? Okay. Yani arabada bir noktada bir model diyoruz ona biz, mod diyoruz. O modda mesela 2 Hz'lik bir mod var. Arabayı mesela çalıştırdığınızda mesela arabanın motoru böyle sallanıyor ya. Sallanmasının sebebi asla değil, yavaş hızlarda dönmesi değil. O frekansla sizin arabanızın frekansı çakıştığı için hep üstüne yük biriktiriyor. O yüzden sallıyor zaten. Aynı köprüdeki gibi. Anladınız mı? Doğal frekans bu. Ve her şeyde doğal frekans var. Mesela benim doğal frekansım var mı arkadaşlar? Var mı? Senin ismin neydi? Yok sen değil. Evet sen. Hayır sen de değil. Senin arkanda. He? Emirhan. Emirhan benim doğal frekansım var mı? Var mı yok mu? Var. Neden var peki? Bir mühendis gibi bunu anlat. Bak şuraya bak. Denkleme bak. Denkleme bak. Mühendissek hep denklemlere bakacağız. Neden benim doğal frekansım var? Başka? Bir de neyim var? Kalbim de var da. Başka? Hocam inancınız da var. Adamsınız filan, artık buraya gidelim. Hız değil bak. Şimdi kütle var orada bakın. Ne var orada? Bak. Kütle var. Bir de bende ne var? Yay var. Bak şimdi herhangi bir şeyde kütle varsa, yay varsa orada ne var? Doğal frekans var. Ne istiyorsun? If you have any process M and K, and so this formula is constant. K divided by M is equals to the WN square. Right? O zaman ne diyeceğiz arkadaşlar? Kütle varsa, K varsa kesinlikle doğal frekansta burada var diyeceğiz. Zaten bu denklemleri yazmamızın amacı bu. Değil mi? Neden yazıyoruz biz bu denklemleri? Zaten her şeyi ortak bir formda çözebilelim diye. Şimdi bakın. Birazcık açıklayayım ben bunu size. Now, this is the case of the what? This is the case of the no loss energy. Or we cannot consume the energy. We store the energy at this case, and so we utilize all the time. But we have the another response. 2.5.6 damped natural frequency. What is the damped, Abdullah? You look so happy, Abdullah. What is the damped? Damped. No. Oh, okay. And so Yağmur. Damped. Damping ratio.
Damp means thrown.
Huh?
Means thrown away or lost.
Lost. We can lose the energy, right? We consume it. And so, which parameter should be added to what the M and K equation? Huh? Huh? Damping energy, but which parameter represent these terms? C, right? But in the real life, for example, if you have the circuit, and so we should use to what the resistor and capacitor, right? And so the resistor is always consumes the energy to converting to the what? To the heat. And so the R, or the resistor value, is equalized with the what? With the damping ratio, right? Because we consume it. We cannot use this energy on the system. We can use the capacitance or the inductance energy, but we cannot use the resistor energy, right? And so, just like this one. You have a question? No, okay. And so, we need to write to the what? To this form. To suppose that M times x dot dot plus c x dot plus k x, right? Or, yes, this is the initial condition form, right? And so, if we consider the x0, v0 is equals to 0, and then this is the ms square plus cs plus k, xs is equals to the 0. xs cannot be equal to the what? To the 0, and so the R characteristic equation or the R response parameter must be equalized with the what? With these terms, okay? And so, how can we find the roots of these values, s1 and s2? Just remember the ax square plus bx plus c is equal to 0. And so, I can write the what? The square root formula, right? And so, minus c plus minus c square plus minus 4 times mk, right? And divided by 2m, okay? Okay? And so, if we recollect these terms, we can write this equation just like this one. A minus a plus minus bj, right? If we choose the what the negative value at the square root form, and so we will yield to the what the b times j. And so we have the minus c divided by 2m, and so this equals to the what? To the a, right? We can write or we can generalize this equation in terms of the what? The a and b, okay? B maybe equals to the 0. But we can write it at any case using these equations, okay? And so, in this case, the A is equals to the what? The minus C to M. Or B is equals to the what? So if we reorganize this equation, and so the K divided by M minus C to M square, okay? We can rewrite this equation based on the A and this B parameters, okay? So, this equation is the what? S plus S1, S plus S2, okay? And equals to 0. And so, the solution, can it be look like to the what? Xt is equals to E minus AT times X 0 times cos BT plus X dot 0 plus AX is 0 B times sinus BT. But this is the case of the what? With the initial conditions, okay? The other not, but in the initial conditions, the R characteristic equation ms square plus cs plus k does not change. Just the constant values coming from the what initial condition x0 and v0, okay? And so, if we evaluate this equation, just see that if the A is positive, and then we can say that this system is said to be what? If the A is positive, steady or stable, right? We are going to the what? To the 0. And so, if we have the cosinus and sinus value in here, and so we can say that we have oscillation, right? This system oscillates. And so, if I guess the response of this system in here, it looks like this one, right? Because we have the oscillation in here, and the t is going to the what? To the infinity value. And so, we will have this kind of time response, right? And so, we have the what? Wm value in here. And also, we have damping factor in here, right? Because if you don't have any damping ratio or the damped frequency, we cannot consume this energy, or we cannot go to the what? The 0, right? If we are going to 0, and so we consume the whole the energy in here. We can oscillate it, but we always consume the energy at the end of the what? The time, okay? And so, just see that the R characteristic roots is equalized to S1 and 2 minus A plus minus Bj. J is always related to the what? The frequency, right? And so if we have the J parameter, and so we will have the oscillation, because the cosinus and sinus is consisted of the what? The J, the imaginary numbers, right? And so this B is the important here. And so this B is equals to the what? The divided by K divided by M minus C divided by 2M square, right? And so this is called the what? The damped natural frequency. The Km is equals to the what? Natural frequency, right? But square form of these things, right? Wn square is equals to what? The K divided by M. And so this is the Wn square, right? And so if we have this damped natural frequency, and so we can say that we have the oscillation, but always we are going to the what? Going to the 0, the stable point or stability point. But what happened if I choose to what? This B value, and so this B always shown into the what? The WD. W damped natural frequency. And so Wn is equals to what? The W natural frequency. Okay? And so if we show this WD, and so we can say that this is the damped natural frequency. Then suppose that if the Vd is 0, okay, and we can say that no oscillation happening here, right? Because we don't have any imaginary roots at this time. If we don't have the imaginary roots, and so we can say that this system does not oscillate, just growing or decreasing, just stable or unstable. Why, Mehmet? Yes, yes. And so if this is the case, just remember the formula: K divided by M minus C divided by 2M square, which is equals to the what? The 0. And so if we take the what? The square form of these terms, and then we can say that the K divided by M must be equals to the what? The C 2M square, right? And so we can take or reorganize the equation in order to what? In order to represent the C coefficient in here, just like this one, 2M, these terms, okay? Or we can rewrite this equation 2KM, okay? See? We can derive the what? Damping ratio. But in real systems, we should select the C value, the damping ratio, guys. And so, what is this value at this case? We define the natural frequency, right? And so, if our input frequency is matched with the what? With the natural frequency, we always store the energy. And we will what? Destruct the what? The bridges or the car, right? And so this value is another important parameter defined with the what? The K and M. This is the critical damping value. And so if our system is equals to this one, and so we don't have any oscillation, and so critically damped value represent that our oscillation is started at this point. If we equalize the WD is equals to 0, this is the first point to start the oscillation, right? You understand that? If the WD is greater than 0, and so we have the oscillation, right? This critical damping, or in another sense, we can say that the WD is equal to 0, no oscillation, right? And so WD is greater than 0, and then oscillation happen, right? And WD is smaller than 0, no, but exponential behavior, because we have the J values, and so we can add what another term of the A value in here, okay? And then if we have this information, or we can condition to what? By using this definition to what? This system is oscillate or not oscillate, or exponential behavior can happen in the system. And so we can divide to what? To 3 property from the what? From this system. And so how can we do that? Just see that this is our parameters, right? And so I can introduce the new parameter, zeta value. Have you heard about anything of the zeta? C divided by 2mk, right? And so if the C is equals to 2.km, which means that we don't have oscillation, right? And so if zeta value is equals to the 1, this is the critical damped. If the zeta is greater than 1, it's overdamped, which means that we don't have any oscillation. If we have the zeta is equals to the 1, it's a critical damped. This is the starting point of the no oscillation point, right, Zina? If the zeta is smaller than 1, what happened? Huh? No, underdamped. Yes. And so in the critical damped, we have oscillation or not, Mehmet? Huh? Yes, no oscillation. Yes, starting or diminishing, right? Because the zeta is going to what? Coming from the 1.5 to the what? 0.5, and so the oscillation does not, but before or the is smaller than 1, and so we have the oscillation. And so if the zeta is smaller than 1, Ulaş, oscillation, yes. Because our rules has the imaginary component, because the WD is non-zero value. And so what happens of the overdamped system? Huh? No oscillation. Because it's overdamped. Çok geliyor yani. Çok. Sen veriyorsun ama yarısı zaten kayıp oluyor. Anladınız? Böyle bir şey yani. Okay. And so if we want to design this system, in order to create the zeta is equal to the 1, we should select the C value to Km, right? And so if we select the C value is greater than 2 km and smaller than 2 km. See, if we have the information about the the K and M, we can create or we can condition our time response by selecting the C value. For example, 2 km is equals to the 10. If you want to create a no oscillation system, Mehmet, what should I choose the C value? 10 or greater than, right? See, it's the powerful information about the system, right? If you know the M and K, Zina, and then we can select the C value, or we have the C, and then we may choose the M and K based on this information before testing it, before designing it, right? We can create or we can build any time response characteristic based on this information. So, yes.
Is it always better to make a system that is overdamped, or?
No, it's purposely selective to the for your application, okay? And so in your application, maybe you require to overdamped system, or maybe you should oscillate at the beginning of the initial states of these values, but after that you can converging to the some steady state point, maybe. And so it's the specific application task selection.
Will there ever be oscillation required, like under damped situation?
Yes, under damped situation. For example, if you have any system with based on the spring coefficient, for example, and so if you run this system, you may look or identify your system performance at the beginning of the oscillation. Okay. For example, if you have any mass spring damper estimation, so you can pull the and so the oscillation may the converting or the special feature for your system. Maybe. For example, in the suspension systems, the overdamped or the underdamped does not select. They are not selected because at this case, for example, if you have driving the car, and so the car must oscillate to feel this power, from the humans, right? And so this is the what application task selection for this one. But if we are using the overdamped system, maybe your system does not give your feedback to the human, right? For example, this is one case. Okay? Örneği anladınız mı arkadaşlar? Yani her zaman için mesela bizim salınım yapmayalım dememiz iyi bir şey değil. Mesela bazen bunu hissetmek isteriz. Bazen bunu ölçmek isteriz. Bu bizim için ayırt edici bir faktördür. Anladınız mı? Ya da bazen gerçekten bu sistemi tasarlayamayabilirsiniz. Sistem buna izin vermeyebilir. Okay? So, we have three parameters, M, C, K. And also, we have the zeta, W, and WD. Right? So, we can create the general formulation about these terms. So, let's remember the what ms square plus cs plus k is equals to the 0. Okay? And so Wn is the what the k divided by m, but in square root, and zeta values is equals to what the c to mk. Okay? And so just divide the whole terms s square with the m and cm s plus km, right? Which is equals to the what? 0. And so what's this value? S square plus c divided by m s plus what's equals to the what? The wn. What's the formulation? What? Yes, this is equals to what? The wn square. And so we have the cm. Just see that this cm, we need to multiply this value s square plus in order to obtain the cm in here. If we to zeta, and so to zeta to c divided by m k, and so we need to also what the k divided by m, and wn s plus omega n square can be written for this equation. The last one and the second one is identical to each other, guys. Okay? See, every system at the second order system is represented by with the what? The zeta, wn, and wd. In this case, we only use the what? The zeta value and the wn value. Wn value is always related to the what? The frequency values or the oscillation pattern for your system. But the zeta value is, Abdullah, is related to the what? Damping. Or it means that the loss energy is identical with the what? With the ratio of the what? The zeta value. And so we can condition the zeta with respect to the what? The 1. Greater than 1, smaller than 1, equal than 1. Right? This is important. And so if we have this Laplace transformation, this is the equation to behave in the what? In the time response characteristics. And so we can check the root values of these terms. Just see that. What is the root values of these things? We have two roots. We have the square form in here. The root form is equals to what? The zeta wn plus minus j times wn times 1 minus zeta square. Okay? And so this is the what? WD, right? And so see that our roots is converted into the what, or transformed into the what? Into interpreter parameter in terms of the what? The time response characteristics, right? And so we can choose the different zeta values or the wn values, and so we can design the RMCK system based on these informations, right? We can select the what? The time characteristics, and we can design RMCK system based on the zeta and Wn values, right? Abdullah, this is a huge advantage to what? To design your system dynamics problem. Okay? Arkadaşlar bakın. Bu genel form var ya, bu müthiş bir şey. Ya bir sistemin karakteristiğini seçip kütle yay damperi bulabilirsiniz siz, ya da bir sistemin kütle yay damperini seçip karakteristiğini çıkarabilirsiniz. Yani biz bir daha sistemi tasarlamadan zaman cevabını oluşturacak kalıpları zaten bundan üretebiliyoruz. Bu müthiş bir şey bizim için. Neden müthiş bir şey? İsmi neydi? He? Zülküf. Neden müthiş bir şey bu? Harika bu yani, anladın mı? Dondurma gibi bir şey yani. Bu çok güzel bir şey yani. Neden ama bu? Söyle ya. Az önce söyledim oğlum. Nasıl fikrin yok lan? Az önce söyledim. Neden bu güzel bir şey? Neden zeta'yı W'ni kullanıyoruz? Hacer. Niye? Evet. Ne yapacağız peki bunlarla biz? Hı. Tamam ama ne yapacağız bunu yani? Ne yapacağız bu zeta ile W yani? So, if we have this information and then just remember we have the S-plane in here. S-plane consists of to what the sigma and J W value, or the real part or imaginary part, right? We have two parts in the S-plane. And so, what is our roots? Just remember the formula S1 and S2 as zeta Wn minus plus Wn1 zeta square times J. Okay? So, how can I put these roots into this plane? I need to put a point or dot. How can I do that? Yes.
The real part is the omega n.
Huh?
The real part is the omega n.
Yes, omega n times zeta. Okay, and so we can draw this zeta times omega n because it's the real part, right? And so we have also a what? A imaginary part, right? And so this equals to the what? Just say it.
Omega n radical 1 minus zeta squared.
Yes. See? This is our representation. And so, if we have this S-plane in here, we can say it. This system is stable or not? Right now. Can anyone say that? Mehmet. This system is stable or not? I'm not sure. So, okay. And so we need to think about it, right? And so, the stability rules means that if our time constants is positive, but just remember that E over minus A times T, right? And so if the A is positive, and so we can say that this is stable. Okay. So, our roots must be negative if we want to talk about the stability, right? If we have this condition, just see that our solution of this formula is equals to the what? E over minus zeta W and T times x0 cos WD T plus V0 plus zeta Wn x0 divided by WD sin WD T. Okay? These are the solution for the what? The S square 2 zeta omega n dot S plus omega n square. Okay? And so, just see that zeta times Wn is greater than 0, and so we can say that our system is stable. Okay, and so this is our root in here, and so at this case, this system, this point is stable or not? This point is stable or not? Huh? Second area stable, but we can say that in a different way, that if we have this property, and so we can show it just this one, right? And so zeta must always greater than 0, because we cannot have the negative zeta value, because it's the directly proportional with the with the C value, damping ratio. Damping ratio cannot be negative. And Wn, we don't have the negative frequency value, and so this value always to what? To what? What? To what? Yes, positive. And so if we have the minus value, and so it's always negative. And so just like the Yağmur said, this area always to what? Stable. And so we can continue with some examples. Sigma and J and W. If I put the minus 5 root, what is the characteristic feature of this minus 5? It is overdamped or underdamped, or the oscillation happen or not? Mehmet, just help me. We put this root S1 and S2 is equals to the minus 5. Yes. This system is stable or not? Firstly, it should be stable because the root has the minus or the negative, right? Okay. And so this system is oscillate or not? Just see the figure. Just see. Why? This equation is equals to what? Zeta Wn. And so zeta Wn is equals to 5, right? We have the zeta value. And we have the Wn value. But we have two terms in here, with the real part and the imaginary part. If the imaginary part does not exist, and then we can say that this value is stable, and also we have the oscillation or no oscillation in here. Yağmur, we have. Abdullah, we have oscillation or not? In order to have the oscillation pattern, we need to have to what, Sarah? Huh? Yes, WD. But the WD at this case is equal to the what? 0. And no oscillation happening here. Right? Because it's on the what? On the sigma axis or the real axis. Right? And so what about this one? Minus 2 and 3. Is this stable or not? Stable. Oscillation happens or not? Yeah? Happens. Oscillation. Right? Okay. And so, what about this point? This system is stable or not? Unstable, right? And so, oscillation or not? Oscillation. Yes. That's good. Okay. And so, what about this one? If we have this condition, this is the minus 2, and since this is the minus 2 point, minus 2 plus j3, and also we can write that this is the point of the what, the minus 10 plus j5. And so what is the difference between the minus 10 plus j5 and minus 2 plus j2? Minus 10 plus j5 has the stable property and also have the oscillation, but these 2 points are different to each other. In which way? No. Damping. Who's talking? Who's talking? Yağmur. These are different parameters. In order to look this property, we just say that. Just remember, our equation is that to what? S1 and 2. Zeta Wn J Wn 1 minus zeta squared. And so S1 and 2 in the first case minus 10 plus J5. And so the other thing is the what? The minus 2 plus J3. Right? And so these 2 parameters are different to each other. So we can draw the what? The time response of these characteristics, xt. And so if this is stable, we have the xss value in here for both what? Time responses. But just see that zeta times wn, one of them is equals to 10, the other one is 2. What is the difference in the time response? The time constants are different. If we have the greater zeta wn, and so the R signal, faster response, right? And so first of all, we can draw this signal just like this one, okay? So it's the 10. And so this is the x1 signal. This is the x2 signal, okay? This is x1. And so how can I draw the x2 signal in here? S2 signal is the what? Minus 2, which means that our response is slower than the first one. But what about this value? This is 10. Oscillation or high or low? High. Okay. Ozone. Okay. And then we can draw this time. I'm sorry. This must be slow. And so it's the slow value. And so I'm rewriting this function in here. And so are the steady state values is happened in here. But in the second case, we have slowest response, just like this one, but we have the higher frequency values in here. Just see that. We have the high frequency value, but the slowest response, because we have the one point in here, the other point in here, right? See, we can condition the what? The R parameters, zeta and wn, in terms of what? The time response characteristics. This is a huge advantage, right? Mehmet, did you understand what I'm saying in here? Okay. And so what happens if I choose the root in here? 2j. What happened? Is it stable or unstable, Hajar? Huh? Why? Huh? Yeah, but this in this case the S1 and 2 is equals to 0 minus 2j. What happened if I choose this root? Huh? Yes, this is possible. See that? We don't have any damping in here. What? We don't have any growing part. or decreasing part. We just only have to what, Ulaş? Sadece ne var burada Ulaş?
Oscillation.
Yes. And so this signal looks like to what? To this one. Neither grows or neither decrease. Right? See? If only have the JW part, and so our system always oscillates. But neither going to what, the infinity or the zero value. It's bounded. Sınırlı. Bounded. Okay? Okay? Okay.